Good morning, everyone. Welcome to our last session on natural language processing in the scope of atoms. You went all the way through the fundamentals and have seen various approaches to learn word embeddings. That is a big accomplishment already, and it probably readies you for many NLP tasks that you might face in your studies and in your working career. However, the progress in NLP or at the interface of deep learning and NLP, it's really fascinating, it's vast, it's massive, and I want to have one more session in which we'll have a look at some of these more recent techniques that have come up and made some further major improvements compared to what is possible in terms of NLP, in terms of language understanding, using deep learning, and this is what this session is all about. So I hope you're as excited as I am, and let's get started. The agenda is as follows. We start with a little bit of an introduction that's slightly longer than usual because it's important to understand why the word embeddings that we covered so far, albeit the fantastic things that they can do, like king is to man, as queen is to women, why they are not enough, or where is maybe room for further improvement. And that will make the case for transfer learning in NLP. And should you have not heard about transfer learning, don't worry, we'll look at that. We get there very soon. And then in the reminder, there are sub-chapters for individual approaches that have come up in order to address the issues of word vectors or in order to facilitate transfer learning in the scope of NLP. And we will look at a bunch of these techniques. And although it's actually, as I said, difficult to really keep up with the progress in the field, I hope that after going through these sub-chapters, you are at least getting very close to the state of the art in the field, and more importantly, even have an idea of what are the challenges that concern scholars these days. But anyways, let's first start with the introduction and clarify this transfer learning bit. That's really the core of the introduction. And for that, it's useful to take a big step back into the long time ago, where we had a slide such as this one. I think it was our very first session where I was trying to make the case for deep learning and showcasing how deep learning facilitates the automatic learning of features. That was the key distinction between classical machine learning and deep learning, that classical machine learning models rely heavily on carefully handcrafted features to carry out a prediction task, whereas deep learning models promise to learn good features automatically through the hierarchical of layers in a deep neural network, where earlier layers pick up more basic patterns in data and deeper layers pick up more high-level patterns in data that can be learned from the basic patterns. And the classic example is this image detection task, where we have a neural network that starts from a raw image, which is just a bunch of pixels with color, and where then earlier layers in the neural network pick up basic patterns, such as lines, or maybe squares, or maybe triangles, basic geometric patterns, which are then fed to deeper layers in the neural network, where these basic patterns are generalized to something more high level, like an eye or a nose, if we envision a face detection task, and where then yet deeper levels learn that if there are patterns that resemble eye or a nose or an ear or a mouth, that is exactly what makes up a face in the end. And it's this kind of task sharing, solving a difficult problem through decomposing it into more manageable individual problems, like that of detecting an edge in an image. It's easier to detect an edge in an image than to detect a whole face. And this is how deep neural networks for image analysis tend to work. they exhibit this type of task sharing. And this picture, the sequence that you see here, this is how it is constructed. You extract the activations from hidden layers in a deep neural network, and that allows you to sort of picture what type of patterns they represent, and then you can find that deep layers in a network, that their hidden units, their hidden unit activation, they really tell you something about faces, whereas earlier layers captured entirely more rudimentary patterns. This really is fundamental to the promise that deep learning is able to craft features automatically, or to pick up features automatically without much human intervention. You feed it the raw image and you get a very powerful face detection classifier or image classifier more generally. And it demonstrably works in the scope of NLP, in the scope of image detection. Allow me a quick detour. We will look at image detection more closely in our last lecture, but to make the scene for NLP transfer learning, it is useful to know a little bit about image models. What you see here is a rather famous image model. You know, with image models, it's a bit like NLP. There is so much progress in the field, and any image model that comes out, soon later, it's outdated. So this model is no longer a state-of-the-art again, but it's maybe still an important benchmark. It's called ResNet. Successful image model, get the name. So this is ResNet. Welcome, ResNet. Hello. And the models like ResNet and other similar type of models, they are publicly available, which means that you can download these models, and it's a neural network. And basically what you see in the picture is that it's a neural network with many layers. These colors indicate that there are certain blocks in the architecture of this neural network. You do have an input and you do have an output, as with any neural network, and in between you have hidden layers. And in this ResNet model you have loads of them, 152 layers in total, which is pretty deep, isn't it? And well, image models often exhibit some recurrent structure where you have blocks that reoccur. We have the blue block, we have an orange type of block, we have a purple block here, and then we have a greenish type of block. That's a blueprint of the architecture of state-of-the-art image models. And the point we're trying to make here is very deep, and it has won a famous challenge, the ImageNet challenge in 2015. ImageNet is an important entity in the scope of computer vision. It's basically a database. It's, I think, the biggest database that exists for images. It's organized by the WordNet hierarchy, which is a lexical database of English, and it groups nouns and verbs of the English language into sets of cognitive synonyms called synsets. And there are more than 100,000 synsets in WordNet, and the majority of these are nouns. And then in the ImageNet database, they collect a bunch of images for each of these synsets, on average providing something like 1K images per synset. So it's an enormously big database. Probably nowadays it's bigger compared to when I did this slide. Here I have 50 million of images, according to roughly 22,000 indexed synsets. You can go to the ImageNet website, which you find at http image-net.org. Probably nowadays it's even bigger than that. Big database as images organized according to the synsets. And every year they would run a competition on this database where they select a subset of the images and then let computer vision researchers and practitioners perform some tasks like localizing an object or detecting an object in labeled categories of images, finding a face in an image or finding a car in an image, something like that. And that is the ImageNet challenge. And it used to create quite some attention in the field of computer vision and it's sort of a benchmark for the progress that's made in the field in 1 year. Here's just one example to make this point that you have a lot of images there. For instance, I found that there are more than 1,400 pictures for the noun banana. Well, that's impressive. Interesting to see that you can take so many pictures of something as interesting as a banana, but it just showcases that you have a lot of data there, various images, and you can use that to come up with image classification tasks for computer vision models. And since one of the tasks, the one I'm focusing on here, is to classify images. Give a model an image, say, is that image showing a banana or not? Is it showing a car or not? And then the label is either yes or no, that's image classification, or you just feed the model an image and say, tell me what's in that image. You could imagine a multi-class model with an output layer where you have one unit for each of the different categories that you are to classify. You have a nice softmax in the output layer, so you get a distribution over image categories, and by feeding the model an image, you get this probability distribution, very much as in language modeling, very much as in NLP. And because you're classifying images, it's sensible to measure the performance of a model using the classification error. And what you see here is how this classification error came down and down and down with every year of the ImageNet challenge. And you see that 2015 was the first occasion where a model, which was this ResNet thing, that made ResNet so popular, was better at classifying images than a human annotator. And this coined, I think, for the very first time, not entirely sure about that, right? Don't bet on that, but achievements like that coined the term superhuman accuracy. You have a model that solves the task more accurately than a human could. And here the accuracy of image classification exceeded that of a human annotator. So you can imagine that this created a big awareness, big fuss in the field. And later on, there were more advancements, and I have no idea what the performance might be like today, but it's probably even or a lot better than in 2016. So clearly there's progress in the field. Errors come down in image classification, and this is really measured according to an established benchmark with ImageNet Challenge. Progress is there. Another interesting phenomenon is that if you look at the type of models they are using, you can observe how they get deeper and deeper. And here again, ResNet was quite special in that it was really an enormous increase in the depth of the model compared to the previous year. GoogleNet was like a 22-layered neural network, convolutional neural network to be precise. We will learn about CNNs later. And then with ResNet, they made this model 152 layers deep, super deep type of model. And well, looking at this graph, you can draw the conclusion that the number of layers, depth, it matters. Which does make sense or agrees with this whole idea of feature learning in deep learning, that you need multiple layers that you concatenate, and where earlier layers pick up more basic pattern, that later layers distill into something more abstract, creating some higher level features, and that goes on and on and on with every layer. And in the end, you have a very powerful classifier like ResNet. So depth matters. Note that we'll need it shortly. Depth matters. That is one of the key takeaways from this detour into ImageNet. One more. Transfer learning beyond Word2Vec and NLP. What is transfer learning? Let's start there. With transfer learning, in general, you just mean that you have a model that you train on a task A, and you can then solve another task B starting from that model. So what proved extremely successful in computer vision is that you take these models that were trained on ImageNet, you take these ResNet, it's just a neural network. It's essentially a bunch of numbers, if you think about it. A neural network, you have the architecture, and then you have these weight matrices. You store these weight matrices. This is what the neural network is all about. You can load these weight matrices from file and then reconstruct the neural network in memory and use it to do tasks, to classify images, for example. That's meant by transfer learning. And it's super popular in computer vision that in order to solve some image classification task or some image processing task more generally, you start from a pre-trained model like ResNet that was trained on the ImageNet database, and you use that then for downstream applications. Maybe you retrain the weights using your data, or it proved quite promising to not even do retraining, but to just use these models as is, and you can solve some downstream tasks that involve image processing using these pre-trained image models. It's the common approach, really. In image analysis, I dare say you would never really consider to build a neural network from scratch. Nowadays, you would probably always start from some pre-trained image model. And when I say pre-trained, the source of data on which image models are pre-trained, that is ImageNet. It's the single go-to source where you can download image models pre-trained on that source. And the question arises, given that it was so successful or is so successful in image analysis, could we have something likewise in NLP? What's an analog for this ImageNet and transfer learning, pre-trained ImageNet models? What is an analog in the scope of NLP? And the first answer that might come to mind here is that, how about word vectors? Word vectors are something similar. You can download them. You can download the Groovy word vectors pre-trained on some type of Wikipedia corpus, I believe. Or there are word vectors trained on news-based corpora like Google News. You can download them. You can use them in your downstream applications. That's also a way of transfer learning. So transfer learning in NLP exists since word vectors are available, which is for quite long. However, these word vectors, if you revisit how they are trained, and you spend more than enough time on a training of word vectors, didn't you? The skipgram approach, the SIBO approach, these were very, very simple and shallow neural networks that were used there. It was a one hidden layer neural network, not even any type of nonlinearity. It was just basic a linear model, big linear model, because we typically have these very big vectors on the input and the output dimension, and our weight matrices from input to hidden and hidden to output also are fairly large, being V by, so vocabulary size by embedding dimension, big. But other than that, it's very simple and shallow neural network. And if you carry out transfer learning in NLP by using pre-trained word embeddings, you essentially use pre-trained weights from the first layer of a neural network. Whereas image analysis or computer vision shows us how using very deep neural networks that have been pre-trained in downstream applications is much more successful, or is very successful. And then couldn't we have something like that in NLP as well? Couldn't we reuse in a transfer learning setting? Couldn't we reuse NLP models that have been pre-trained in some way that is generically useful useful in many NLP tasks, and where the pre-trained model really is a deep model, so that over the sequence of layers, some high-level type of patterns could have been learned and can then be reduced in the downstream application. That is the goal. That the goal for going beyond word vectors. And then to get there, we need a task that is a bit like ImageNet, or we need something like ImageNet but for NLP. Image classification on this enormous database that is the thing, as I said, for pre-training image models. We need some equivalent for NLP. We need a task where we learn features from the text data that are very likely to generalize to new NLP tasks. The whole idea of pre-training is that you face a problem, you face a downstream task, and you reuse something that helps you with solving that task. And it turns out that in computer vision, models trained to classify images are useful in downstream applications and can solve other type of image tasks pretty well. So you need a task that resembles image classification in NLP. And also the ImageNet database is big. It's really big, so you need probably a data set that is large to pre-train NLP models, deep NLP models. A deep model has many weights. To tune many weights, you need a lot of training data. You also need a lot of resources. That's another matter. And data quality typically will play a role. At least the creators of ImageNet, they invest great amounts of effort to maintain or ensure very high quality of the image data. And I mean, if you think about the previous picture here, have you ever seen so beautiful pictures of a banana? Probably not, right? I certainly have never taken as nice a picture of a banana, but then I don't seem to remember myself taking so many pictures of bananas anyhow. But data quality, that matters. Okay, so that sort of created a moment of thought, like what could we use in NLP? What could be our task to do pre-training? What's the NLP task where we exhibit these characteristics, where we have a lot of training data, which is high quality, and where, well, we solve a task that is likely to be useful in other NLP tasks. And then you can go through a list of common NLP tasks, like there is the task of reading comprehension. That is, you train a model to identify a passage in a text that answers some question. So the model gets a text and the model gets a question. Both are text, and you feed these two bits into a model, and then you want the model to predict probability distribution output what parts of the text are relevant to the question. That's reading comprehension. Or there is text entailment, where the model is to identify relations, such as entailment or contradiction or neutrality between a piece of text and a hypothesis. Does the text support my hypothesis? Deep learning is cool. That's a hypothesis. I can feed my model a bunch of text and then ask it to give me a signal whether the text is in agreement with my hypothesis. I should better call it an opinion, because it's not strictly speaking a hypothesis in an academic sense. Anyways, that's also a standard task in NLP, and it is a task where we do have data. Same with reading comprehension, there is data available. Machine translation may be the most studied task in NLP. There is a lot of data available, because training data sets to translate from English to French, from English to French, from English to German, German to French, there are a bunch of training data sets for machine translation. That's also a candidate application. And then there are more. There's named entity recognition, there's POS tagging, semantic role labeling, etc., etc. There are a bunch of standard NLP tasks, and the question is, which of these tasks really is the one that gives us as good results when we do pre-training as we see in ImageNet where we do image classification. Which task is the most representative of the space, the whole space, that's challenging, of NLP problems, and facilitates learning most of the knowledge required for understanding language. For pre-training, it's a goal that you want to pursue, building a model that understands language. If you have a model that understands human language with all its complications, then no matter what NLP task you face in the end, likely that model will be useful and contribute to you solving your task, if it understands language. So which of these tasks really help you, or no, which of these tasks really let you train a model to understand language? And to not make this too exciting, the answer is language modeling. That is the answer which scholars agree, that is the task, language modeling, that shows all of these features that we need. For instance, training is typically organized, as a minimization problem. We do need some sort of labels that we minimize, albeit the excessive and prohibitive costs of human annotators, they might introduce bias, which then a model trained on a task where you have labeled from a human annotator might simply pick up the human bias. In fact, there is fascinating research that was published in Nature, I believe, how NLP models pick up bias in human language. I'll try to remember that and make the paper available on Moodle, but if you are interested and you Google for bias, language, NLP, probably you'll find the paper pretty soon. It was either Nature or Science. Anyways, so for language modeling, as you know, we don't need any human annotators. More facts about language modeling with regard to, does a model that's trained to do language modeling, does that model really understand text? If that's the guiding principle, does being good at language modeling really indicate that a model has understood text? And to some extent the answer is probably yes, at least a good language model that needs syntactical and semantical understanding. And if you take as an example the sentence, the topic of the lecture was interesting, but the lecturer was, and then remember the task of language modeling, given the sequence of words, predict me the next word in that sequence. So what's the word following the was here? What's the word to plug in where we see the 3 question mark? And now to come up with a good forecast of this next word, the grammatical form of the predicted word should fit. So given the sentence, it's quite likely that we need an adjective here. A noun doesn't really fit, nor does a verb. So to make up a prediction, our language model has to understand that, given the input sequence, the next word in that sequence is likely to be an adjective. So considering a probability distribution over a full vocabulary, we would like our language model to assign much higher probabilities to all the adjectives compared to the nouns and the verbs or the prepositions. Prepositions is maybe delicate. I could easily imagine some sentence here. Anyways, grammatical form of the predicted word must match. Generally, that's true. Our model must also realize that the next word, and that's much harder, the next word in the sentence is to characterize the lecturer. We need an adjective, but this adjective is to characterize the lecturer. That follows immediately from the sentence. The next word is not to characterize the lecturer, nor the content or the topic of the lecture. It's going to characterize the lecturer. And the language model must understand that to come up with a good prediction. And then it must have an understanding of what adjectives might come to mind here, what adjectives or attributes are appropriate or likely to characterize lecturers. Boring, for example. Childish, for example. Exciting was great, but I would like to come up with examples like great and fascinating and knowledgeable. However, our model must also understand that this word "but" here, that's a valence shifter. It shifts the positive tonation of interesting into something that's more negative. So probably great, exciting, fascinating, knowledgeable are not the adjectives that should receive a high probability. And yeah, boring, confused, unprepared are the kind of adjectives that would, with higher probability, fit in here. In that they sort of are opposite to interesting. And if you think about it, that's quite a package of requirements, and a good language model would need to meet all these requirements. So yes, with regard to making sense of language, understanding language, good language model needs this capability for sure, which we hope is useful in a variety of NLP tasks. And how about data availability? Oh, that's great, because we have loads of data. Any data set there is, we need no labeling whatsoever. We have SIBO, we have skipgram, or Groovy and others. We don't need to label the text that we put into a language model. The labeling is for free, because we're predicting the next word in a sequence. So no problem with the labeling whatsoever. And are there large data sets available of high quality? Yes, there are. There is loads of data. There's probably more data than ImageNet could ever contain when it comes to language. And current corpora are Wikipedia or news corpora. There are loads of corpora, collections of language, which can be considered to be of high quality. On average, an article in Wikipedia, as far as the language is concerned, shows good quality, right? And if you imagine a corpus of newspaper articles, there are big news-based articles, proper news is also written in a high quality type of manner. The language exhibits good quality. So we have loads of data, and we also have quality data. Well, long story short, empirical findings confirmed all these considerations, and then language modeling became the task, the single task for, not the thing, the task for NLP transfer learning. So the question becomes, how do we do NLP transfer learning based on language modeling? And we can refine that question a little bit. How do we reuse a pre-trained language model, the weights of a neural network pre-trained for language modeling? How do we reuse these in downstream tasks? And that is a question that clearly is of relevance today. On this slide, I suggest two answers to these questions. One is called ELMo, and the other is called ULMFit. And these approaches are proposed in two popular papers, both of which came out in 2018. By normal standards, that would mean that these approaches are fairly recent. Normal scientific standards. If you cite a paper from 2018 in your master's thesis, it's absolutely fine to write something like, recently it was shown that, and then XYZ 2018. That's perfectly fine. If you spot that in published papers, you will easily find papers that make this argument, recently it was shown, and then cite a paper from 2014 or 2012 or even 2010. So by normal standards, these approaches are super recent, but not so for deep learning and not so for NLP. In fact, I was considering to take out both ELMo and ULMFit, since the current status quo does not really use any of these, nowadays, if you do transfer learning, you face an NLP task, you reuse some pre-trained model, quite likely you would not use ELMo, nor would you use ULMFit. However, these two were some of the first approaches that allowed transfer learning in NLP using, well, deeper neural networks. So those were the first steps, you could say, steps that were made toward introducing something like ImageNet and pre-trained computer vision models to the field of NLP. And therefore, I believe they deserve recognition, or they definitely deserve recognition, but they also deserve that you know a little bit about them, which might also be helpful to appreciate and understand later techniques, which we'll also look at. All right, so just briefly, before diving into the corresponding chapters, ELMo is essentially a feature extractor. You train a language model on a large corpus, of course, and then you add the pre-trained representations as auxiliary features into your downstream model. So your downstream model has a bunch of features, whatever these features are, and then you add to these the ELMo embeddings, so to say, as auxiliary features. And a nice feature of ELMo, to jump a little bit ahead, is that it trains embeddings in a contextual way, so that words that are used in different contexts have different embeddings. Like the word bank, which can be the device you sit on, but can be the financial institution as well. And so bank in ELMo receives two embeddings that depend on the context in which it is used, which is pretty exciting. And the ELMo paper was one of the first to introduce that to NLP, contextualized embeddings. And ULMFit is more similar, I believe, to how transfer learning in image models works. And the focus of the ULMFit paper really is on organizing the transfer learning and different stages in which you pre-train and later apply your model. In a nutshell, you first train a deep language model on a large corpus. That's something that is typically done for you. So that's really the pre-training. And then you download this pre-trained model, which is like the first part, and then you fine-tune that model on your corpus that has your target data as a language model. So no matter what your task is, you take the ULMFit embedding and you retrain the weights on your target corpus. And you do this retraining as a language model. And there are some clever adjustments to ensure that in this fine-tuning of the ULMFit language model on your data, you don't hurt it, which could be the case. And lastly, you take the language model, the deep language model that was trained on the big corpus, then retrained, fine-tuned on your target corpus. Then you use all that, but you do another step of fine-tuning. This time, however, not fine-tuning as a language model, but fine-tuning as whatever your target task is. So, for instance, if in the end you want to classify text, if in the end you want to do sentiment analysis, in the last step of ULMFit, you would train your model to do sentiment analysis by just building a softmax classifier, feeding it a bunch of text with a known sentiment label, and let the pre-trained model learn these labels. That's how ULMFit works in a nutshell. And before moving any closer onto the state-of-the-art, we will investigate both these approaches in a little more detail. Starting, of course, with ELMo, which I think was the approach that came out first.